Thank you for the introduction, and glad to be here in the closing session of the excellent conference and follow up on a lot of excellent presentations and speakers, including a lot of people who I learned from in my career, includes a lot of mentors here as well for me. So it's an honor to be here. I'm going to talk about some testing we did, mainly focus on some testing we have done here recently at ENCRI as part of a large collaborative project involving UC San Diego, Berkeley, University of Michigan, and with the core funding coming from the US side from NIST, and then also from ENCRI. And it's on the hybrid simulation of steel moment frame structures with column shortening. We had Professor Wong talk about a little bit about the implications in terms of design for steel structures, in terms of looking at the behavior of steel columns. And I'm going to focus my presentation more on my more comfort area, which is hybrid simulation. And talk a little bit about some of the results we've been getting and what we're doing different, for example, from some of the work that Professor Wong presented. And so this work really stems, if you look at what Professor Wong presented, he tested a lot of individual column tests. And they've done, I think, somewhere on the order of 50, 60 columns at UC San Diego. And what we're trying to do here is take it to the next level, looking not only at individual columns, but test entire building systems. And perhaps the most appropriate way or the most realistic way to do this would be using shake tables. And there's been some phenomenal tests done on shake tables, including at eDefense, at UC San Diego, as well as here at ENCRI in the Tainan labs. And this is, what, if we had unlimited resources, probably what we would like to do. But we've been looking more at using hybrid simulation as a more economical way of trying to explore that system level behavior of structural systems. And it provides some advantages in the sense that it's cheaper, more economical. We could test a larger variety of structures. For example, in shake table, you do one specimen, you're done. Here, it's cost less, and so we can look at variations of parameters of the structure experimentally. And so we had Professor Jim Rickles talk a little bit earlier about hybrid simulation, and specifically looking at a lot of real-time applications and algorithms that they've been developing at Lehigh University. Perhaps I think that's probably one of the more active groups right now in hybrid testing. And we're doing something a little bit different here in terms of looking at not necessarily real-time, slow tests, but trying to apply it to larger, more complicated structures. And so we looked at testing, for example, a moment frame structure. You could take part of the structure, not just a column, but a larger subassembly, and combine it with detailed models of the rest of the structure. And they have the experimental and numerical hybrid model interact to try to get that system level behavior. And then you have your components. The experimental parts are key items that you really want to investigate, that you want to learn more about how to, or maybe not necessarily sure about how to model those components. Another main advantage to shake table testing is that it's much easier to test to failure. Because the shake table test, you got to have that inertia load. And I know, like at UC San Diego, and much like any other labs, the lab managers don't like it when you want to take this inertia mass crashing down on their table. So here, the mass is simulated numerically. We simulate the inertial forces numerically, so we could do a much larger test. Much larger test and push it all the way through collapse. Just as an example, some of the past tests and a lot of the methods that are kind of I'll show later are kind of started developing here in a collaboration with Professor Nakashima. This is while I was still in Buffalo. There was a collapse test in 2007 at eDefense on the full-scale moment frame structure. And if you notice, the picture on the right shows the collapse mechanism all in the first story. And so this is, we don't need to build the entire structure to learn this. We could just test the first story and figure out, try to, maybe get the same type of experimental data as a shake table test. And so we did that. We modeled the specimen. Shake table test was 3D. We went with the 1D test, part of the specimen in Buffalo, part of it in Kyoto University in Japan. This is, again, a collaboration with my research group at Buffalo and Professor Nakashima's group at Kyoto, and did this kind of different substructuring strategies, and we were able to get pretty close to the shake table test. Again, this was a 1D compared to a 3D shake table test. and looking at just a planar structure, not including all the non-structural components, et cetera, that were included, but we were able to catch for the design level tests. You can see on top how we were able to match the motion. I mean, it could be better probably, but if you repeat the shake table, you're probably looking at the same amount of variability in the shake table test as well. So, and we're able to get the collapse mechanism of the structure. So this was pretty important in terms of validating a lot of the hybrid testing methods that we're looking at applying and looking at how well it compares to shake table tests. Now, for these tests here, as part of this collaboration with especially with ENCRI, we've been looking at the behavior of deep columns, looking at evaluating the behavior of these deep, slender, wide flange steel beam members that, when subjected to combined lateral and large axial loads, are prone to buckling locally and globally, as Professor Chang Wang showed earlier in the session, and they're prone to shortening. Right? So we're looking at how do we capture this interaction with the structure. There's a lot of things that could happen. Axial load starts to shift, and is this kind of a progressive failure that goes on, or does a column begin to shorten? Does it help itself by reducing the axial load, and then the shortening arrests? So we wanted to look at this problem, and we've been working a lot with ENCRI because ENCRI has been looking a lot at this. There's been a lot of testing going on looking at this issue as well as looking at column shortening led by Professor Cho here. And so we wanted to test, we designed some building models, and we wanted to test to capture this sort of overall behavior, how this, not just a column, but a complete subassembly interacts with the entire structure, and to try to better understand that system level behavior of the specimen. I forgot to mention here, there's been a lot of column tests, like I mentioned before, and also a lot of numerical simulations. This you could predict a lot of this failure with numerical, detailed finite element models, but I don't think there's available elements like, say, in OpenSeas that could try to capture this type of behavior. So that was kind of the objective of what we wanted to do, and start seeing kind of again some of that interaction as the column begins to shorten, how it moves through the system behavior. And so there was a lot of testing concurrently going on here at ENCRI on these subassemblies, including this 2-column one. It's hard to see around all the experimental setup, but there's been a lot of testing on wide flange and box column specimens going on at ENCRI, and it provided a very unique collaboration, especially in sharing of the test setup. In doing one of these tests, the test setup typically costs more than the specimens themselves, and so it provided a unique opportunity. We started collaborating early on and applied some of the algorithms, for example, that we've been developing in some of the testing that were done on specimens designed to Taiwanese standards. That work has already been published, applying this mixed force displacement control strategies, for example, and there's a paper already on this work. For the U.S. side, which is the part I'm going to focus on, we looked at testing 4 full-scale cruciform subassemblies. 2 were tested quasi-statically, and 2 were tested using hybrid simulation. And I'm going to talk more about the hybrid simulation test and really focus a lot on kind of the developments of hybrid simulation to be able to achieve these tests, including some of the advancements in the test methods. So we did, again, 2 quasi-static, 2 hybrid simulations. There was a lot of change in the parameters on the way because different things happen in the experimental program, some of them which I'll talk about, but the order perhaps we wanted to do quasi-static first. We had some changes in the test setup that led to this configuration. Some real-time changes as we were progressing in the test setup. But we had 2 buildings designed following US practice. The columns we selected were columns that were tested extensively at UC San Diego, the individual column test, so we could be able to compare the member level test later with the subassembly test. And so they're the design of the 2 buildings. As you notice, I'm not going to focus too much on the steel parts. I think Professor Wong covered that a little bit on the implications for design, but focus here more on the hybrid testing and some of the novelties in the tests that we did here. And for one, I think this collaboration really expanded the capabilities of hybrid testing, and especially extended the capabilities of testing that has been done at ENCRI. This is when I was coming up learning hybrid simulation. I learned a lot from, for example, Casey Tsai, a lot of the work that's been going on here in the development of the framework for hybrid testing, and it's really a good opportunity to work here and kind of build on the platform that has been developed here. We looked at using for the numerical modeling this is for the U.S. design test. Looked at using OpenSeas, integrated OpenSeas with OpenFresco, communicating with the speed go to target PC, and then talking to the specimen and sending data back and forth. We also include, and this is a very beneficial part of the test, to include some model updating that I'll talk about, and collaborated on this part with Tracy Becker at Berkeley, as she's been working on some very nice algorithms on that aspect that she's going to talk more about in her presentation that's coming up. For the test, we did an overlapping approach with the substructuring. So we had one specimen. We had 5 columns. We had this very nice setup available. Unfortunately, Director Cho could not satisfy us in getting 5 different columns that we wanted to test at the same time. I'm not sure why. He's a director, but he could only provide one specimen at a time. And so what we did is we tested one column. We saw that the axial load variation drift was very similar on the 3 intermediate columns, and so we had that one specimen represent the 3 interior columns of our specimen. And we used different strategies. We also only had one horizontal actuator on top, and so we really had to adapt to the test setup in terms of our hybrid simulation strategies and substructuring. Our numerical model was very detailed, using some of the more advanced elements in OpenSeas to model these elements. I will point out one key item that we did for the updating. If you look at the numerical model, we got the panel zones, the lump plasticities for the beams and columns. We used the Ibarra-Medina-Krowinkler model for all the upper stories. In the lower stories, we used a Book-Wen model, a much simpler model, but this one had updating capabilities, right? And we only chose the lower stories because we're going to measure a beam hinge in the experiment, and especially all the hinges in the lower story, we're going to go through a similar loading pattern, right? We could have probably done it for the upper stories, but they're probably going to experience a slightly different loading pattern. So we only updated the hinges for the numerical model on the beam in the upper stories, and I'll have a more detailed slide on that a little bit later. For the control of the actuators, basically what we want to do, our key element we're focusing on is the column. And so our control points were mainly the top of the column in the experiment, and we had the displacement that we get from the numerical simulation noted at D1, a little bit smaller, but at D1, we want to apply that lateral drift even with the actuator on top, but the control point is actually, we want to match the displacement right on top of the column and the column to panel zone interface. And then the other thing we want to apply was the axial load on top of the column. And for that end, we used force control. And that was loaded with jacks on top of the subassembly. The feedback to the numerical model is the moment and shear, where we cut each column. So that comes below the panel zone, and the numerical model, we're returning the moment and shear that we measured through equilibrium of the 4 actuator load cells that we were measuring. And also an equivalent force as part of a kind of a unique setup that we had as part of the setup. Now, we used in the axial load direction, again, when you look at displacement-based frameworks for OpenSeas and mostly all finite element programs are displacement-based, where you send displacements to the elements, get back forces. And so this is the typical framework used for hybrid testing. But in the axial direction, the column's fairly stiff. Displacement control is a little bit more challenging, especially in our case. We were using hydraulic jacks because of the high load that we wanted to load. These were more readily available in this lab. And so our displacement control was really bad, but with force control, we were able to get a much better match. And the other thing that has typically been done, because axial loads are stiff, degrees of freedom, the feedback is typically ignored, right? And so one of the things we did in this setup was have this kind of additional control loop to send, so we would send the force, apply the force on the column, and measure the shortening in the column that we're expecting, and then apply an equivalent force on the numerical model to try to match that that displacement. And to get it to match, I mean, there's probably different algorithms we could use. We use a PI controller to try to match that displacement. And this load test, it worked really well. If we wanted to do real time, we might have to look at other options later on. But this method turned out to work really well. And just to show you, because this is kind of one of the key novelties I think we did with this test, if you look on the right, the column shortening, that we're measuring in the experiment, and then in the red, you see the committed displacement in the numerical model, how that displacement is matching, not perfect, but pretty good. The plot on the left, if you look at the blue line, the axial force, that axial load begins to vary somewhat or drop on the column as the column begins to shorten, right? And so this is for it's a pretty high level test. And so we started to get some axial load distribution. This probably had some effect because of the three columns we were assuming shortened the same amount in the simulation. Right, I think 3 columns would have been ideal, but again, we only had 1 as part of the setup. The other algorithm we added on top of this, and this is, there's been some large-scale applications of model updating, I think, including some at Lehigh that have been applied. But this is, I think, one of the more complex applications in terms of degrading behavior specimens and so forth. And maybe there's more work going on that I'm not familiar with, but this is, I think, one of the more advanced applications of model updating at this large scale for this setup. And so basically, because we had in our specimen, we had reduced beam sections on the element that we're not really using them as part of the substructuring strategy, but because we could measure the hinge, we could actually send back and update the models in the numerical element. And that helped quite a bit in terms of actually the substructuring strategy and getting a better correlation between the numerical and experimental model. And so we were able to apply or measure with very fine displacement transducers the rotation at the hinge, and then with the actuator here, we could get the force, get the moment rotation behavior, assuming a plastic hinge length. We could measure the data, update our modeling parameters in real time, and then update the model parameters on our numerical model for all hinges. Right? And again, this is Tracy Becker, I think in the next presentation is going to talk more about other applications of updating that she's been working on. So for the results, we had, these are just kind of overall glimpse of the results that we obtained. So we were getting drifts, we were applying axial loads, I think this was on the order of between 20 and 40% of the axial capacity of the column in some of these tests, and getting drifts for design level motions, for MC level motions, up to like 3% in one test and 5% in the other tests. We selected the ground motions in a way to get the response we wanted to be within the limitations of the test setup and so forth. And to give us the monocyclic, kind of the, to mainly keep within the drift, and also looking for motions that we thought would provide significant damage in the structures. So just some results, just some key overall results of the test. In the quasi-static test, going to 4% drift, this is the amount of damage we saw in the column. And in the test, similar amount of axial load. The test only went to 3% drift, but by this time in the quasi-static test, we had quite a bit more damage. This was to the design level. But even when we went to 5% drift, we saw a lot less damage in the earthquake simulations compared to some of the quasi-static test results we were seeing. And this is, I think Professor Wong actually showed a clear image of this column here. You see the kind of the local buckling effect going on there, the global buckling of the column there in the specimen. And in the hybrid simulations, we saw very little damage in the columns. Again, we couldn't correlate really load to load in some of these tests because we adjusted one of the parameters we did adjust in real time was even the axial load, because one big problem was with this global buckling phenomenon going on here. This carried up to the top loading beam, and the whole thing started to tilt. So we had to be very careful about the level of drift and level of axial load that we're applying to the specimen. But nonetheless, pretty large variations in the response we get between the quasi-static and the hybrid test, even in terms of shortening, going almost 100 millimeters in the quasi-static loading, and going even up to design level and MC motion, going up to maybe about 20 millimeters of shortening in the columns. Right. This a video to show on the mixed displacement and force control. You'll see. So this is a video that's going to start playing, but you see the axial load command to the actuators on that's tracking, the displacement, the measured displacement, and how it tracks with the numerical simulation. It's easier to see the displacement here compared to the drift, how that's varying, and the shortening that's happening in the columns. This initial jump here is just from the gravity loading a load, and then as we go to the MC motion, you see a significant increase with the pulse in the motion. Okay. So this is this is a hysteresis going on at the base of the column. So you see we have significant yielding in the column beams as well. To look at the performance of the model updating, we're going to show here a beam in blue using the IMK model, not updated, but this one has degradation incorporated into it. A more simpler bulk WEN model here that's updated with parameters. And over here we see that the experimentally measured beam moment rotation behavior and how we're calibrating those parameters to those, how those parameters are being updated online during the test. So these are, again, very complex tests. They were a lot slower. I think we're going about 100 times slower than real time. I don't remember the actual time step we used. But it shows kind of the performance of the updating. And this is a design level test and then going to the MCE level motion. And so you begin to see some differences in the advantages of using the updating. We have a model that more closely resembles, this is our calibrated model, how we're fitting the parameters here to the experimental data in real time, and then using that to update the rest of the hinges of the model. Somewhat unexpected, but some of the other things we saw in this test, and this is one of the reasons why we shifted around the test rotations, but we did observe some fracture in the beams early on. And even in these cases, right, the model updating was able to capture that fairly well. And we were able to kind of even update our parameters, because one issue, for example, was if our updated model captures this effect, this is going to propagate to all the rest of the numerical beam models. And they're not all likely to happen at the same time. They're not all likely to happen, especially if you have the bottom flange in tension or in tension when they're fractures, and the other sides are in compression. That's not likely to happen. So we had to be careful and came up with an algorithm to try to determine how and at what time we needed to update the models. So the updating overall, I think, helped to even improve the numerical prediction of the model overall, and especially the correlation with between the numerical and the experimental model, and it really helped the substructuring strategy that we're applying to get a better match and overall more realistic results from these hybrid tests. So to close up, again, the focus here, I think we're getting significant knowledge on the behavior of steel structures, but this presentation, again, is focused on the hybrid testing because we've seen other presentations on the steel, and then we're going to see another presentation on the updating as part of this larger collaborative effort. But I think through these tests, we're demonstrating that hybrid testing can be a very cost-effective way of conducting these tests, being able to test multiple specimens for a fraction of the cost that it would take to get the same information from a shake table. And for these particular tests, I think we pushed the envelope a little bit in terms of the mixed displacement and force control strategy, especially being able to capture the axial shortening. That, at least to my knowledge, there's been force control, but not with the displacement feedback to capture the shortening effect in the numerical models. And again, I think one of the more complex applications of model updating within a structural system. We're still kind of working on a lot of the analysis of the data to try to understand. We just finished a test earlier this spring. And so processing data to compare, for example, how these results compare to the individual column test, And so there's still a lot of ongoing analysis in terms of trying to get better interpretation of these results, and in terms of the behavior of steel frames. Again, on the U.S. side, this award was supported by NIST and working with the University of Michigan. Michigan is a primary. We got a sub-award to UC San Diego, and then collaborated with Berkeley on this aspect on the hybrid testing, and very fortunate to be able to work with NCRE on this project and push the envelope. In terms of the application of hybrid testing, again, we're doing a lot of new things, and we're very grateful to Andres Schellenberg and Javad Hashemi, who helped us a lot when we got stuck in terms of the implementation, in terms of the hybrid testing. And I want to especially thank NCRE for all the support, hospitality, and everything provided during my many visits here in the last year. With that, I'll open it up to questions and listing a lot of our collaborators here on this project.